Hello participants, I, Dr. Sunil Saimal, Organizing Secretary of this event, welcome you all. This is the International Training and Internship Program on opportunity for R&D ecosystem and tech-driven startups. We had started our program on 20th June and will finish on 15th July. The event is organized by Tulas Institute and Tech Counselor. The event is co-organized by Krishna Institute of Medical Science, deemed to be University Maharashtra, and this event is sponsored by TQ3 and Uttarakhand Technical University. We have our industry partners like Yuvayana, Tech and Craft, Swachh, Neer, Boudik Venture, Kaviraj Foundation. Till date, we had many eminent speakers from academic and industries like Dr. Fabio Messi, Mr. Madan Kanala from Canada, Dr. Raman Sharma, senior scientist from Neer, Dr. Rajkumar Haldar, CEO founder of AVNI Biomedical, Dr. Manoj Kumar Panda, Professor, Triple E Department, GBPU Podi, Mr. Naveen Kumar, Research Engineer from France, Shiv Prasad from Bangalore, Mr. Abhishek Gupta from Hungary. We had many sessions of on IoT and embedded, and Vinesh sir took all these sessions. And next few days we will have many other eminent speakers from graphic era like Sakshi Gupta ma'am, Renu Thaplyal ma'am from Tech Counselor. Today we have with us Dr. Yashodhan Mandke, and I am handovering mic to Mukesh to introduce today's expert. Mukesh?
Yes, sir. Thank you so much, sir. Am I audible to you?
Yeah.
Yeah. Thank you, Dr. Samuel, for introducing the seminar, and as well as for introducing the all organizer and co-organizer for this program. I am Mukesh, Technical Research Advisor and co-founder to the Tech Counselor Group. I welcome all the audience for this international training and internship program on opportunities for R&D and tech-driven startups. So we already had 14 session, and today we are having our 16th session on astrophotonics for space R&D, commercialization and application to astronomy for space exploration. Today we have Yashodhan sir with us. I welcome you, sir. He is the Senior Technical Advisor to the Tech Counselor and IoT Head to the Front Lab Group. With core expertise on domain like computer vision, IoT, embedded computation, electromagnetics, and photonics, machine learning, image processing. He's having an experience of around 10 plus years on these technologies. His core area of interest is deep tech, astronomy, photonics, IoT, ML, and some of courses he has done includes Galaxies and Cosmology from California Institute of Technology, USA, Introduction to Astronomy from Duke University, USA, Control of Mobile Robotics from Georgia Institute of Technology, USA, Machine Learning from Stanford University, USA. He has also worked as research scientist at Palhad Ki Chhabaria Research Center, an initiative of Pro Foundation at Pune. Also, he has served as principal researcher to the Terra Research Institute India Private Limited, Pune. Some of the major projects he has worked upon are Cube satellite development with ARM-based platform for the weather monitoring, which include design of sensors, interfacing, signal processing, RTOS implementation, RF and navigation system design, antenna design fabrication, satellite tracking and recovery. Also, he has He's one of the major projects which include free-to-air STB design for Intelsat, IoT development for Hue pattern system, product design with ESP8266 platform using DNS implementation. He also has supported and coordinated Aspire Camp organized by I2IT Pune, which is funded by DST Government of India, New Delhi. Today he'll be having his session on astrophotonics for space R&D commercialization and application to astronomy for space exploration. We welcome you for the session, sir, and I'm very much sure
Thank
and hope
you.
that this will help our participant and our audience to explore more opportunities and possibility into this domain.
Yes.
Handing over to you, to you, sir.
Okay. So thank you, Mukesh and Dr. Sunil for inviting me and giving opportunity to talk to students and other participants regarding this. And let me start with the presentation and discuss go in detail. So, is it visible? Is it possible to see my presentation? I shared. Can you see that? Yeah.
Uh,
Okay. Is it? Can you?
yes, sir. You can put it in the. Okay, this is in the full screen mode. I can see
Yeah.
astrophotonics in the first slide.
Yeah. I'm just putting that. Just a moment.
Okay.
Actually, I have created a PDF as well, so better than sometimes. Just a moment. This document reader is. Okay, let me change it itself. So I'll just put. Some issues with my keyboard, so I'm not getting full screen.
You can put the slideshow on, and I think we are able to see your
This
screen.
is okay?
Yes, sir. Yes, sir. You can put the
Yeah,
slideshow mode.
it's fine, right? Okay, regular mode. I'm just keeping it. Okay, so thank you everyone for having me over here, and I'm giving you opportunity to talk on the different topics regarding this. Of course, like I had discussed with Mukesh on what topics to discuss, and I heard that a lot of people have already discussed about IoT and embedded systems, which I could have other way, like sometime next time I can discuss more about on this industrial area and everything. But this since this is again based on the research and development, part, I would like to do some idea on something about astrophotonics topic, which I think most of very few people are currently working on this topic, and it's a topic like which connects majority of other science science field and engineering technology together, and you can have a lot of research and development in the future perspective. So to start with, so our flow is like what actually mean by this astrophotonics and why do we need it and what is importance of that. Then we can slowly go into this what type of designs and applications. This is like applications that we can have with this astrophotonics technology. So I'll be separating these two topics differently and discussing, and then start merging the things together so that everyone from the engineering background domain can have interest towards it. And of course, this is going to be overview. I'll make sure that I do not put heavy equations that put the audience on the sleep. So this is just an introduction of the topic. It's a very vast topic. So I'll just touch up the key points into that while discussing over it. Okay. So let's start with that. Of course, based on why this astrophotonics. So first of all, as you can see, the market is the industrial market is changing rapidly in terms of if you observe from past 3 to 4 years, the level to which the IoT or machine learning market has changed. It's a drastic, huge development into that thing, right? So IoT has entered into the industrial, industry 4.0 and whatnot. Now everyone is talking on that thing. Now, as the market needs to be continued, continue to grow. The one thing that everyone is interested, whole the globe is interested in exploring space, right? And exploring space gives you a lot of understanding of the universe and other resources that is helpful for the humanity in the long term. So starting from designing of the satellites to exploring the galaxies, everything has been the part of now exploring the space. And possibly I think a week or two back, the chairman of ISRO has said that okay, the private industries can now jump into the satellite market, which was the block for several years in India. So if you go abroad, you see this market is huge open, and there are a number of private companies jumping into the satellites and these aspects. So based on this, I'll start look. So this is one of the area where space exploration can go very long way in different aspect. So starting with what does astrophotonics mean? So basically, you can see it's basically astronomy and a combination of photonics. So what does it mean to us basically, right? Of course, throughout the complete lecture, I'll be explaining these things in detail. But when we are looking at exploring the space through like in terms of the light, in terms of electromagnetic wave, right? So we need a proper instrumentations that gives you a detailed information about the space, and that gives a real good inference in terms of what is actually happening around the space, like outer space, outer planets, right, in our solar system, galaxies, and whatnot. So space exploration is one of the key things associated with this astrophotonics, and where these things are getting connected. So first of all, majority part the exploratory is over the globe that we have a telescope. Starting with if someone has interest in telescopes or astronomy since childhood or so you must have seen or observed a couple of stars, galaxies, or possibly you must have seen kind of eclipses through your telescopes in your school days, or someone must be doing it. I still do it on my own because I'm an amateur astronomer. So these things, give you a lot of interest how these things work around it, and telescopes not limited to only for as an amateur and hobbyist thing. It has become more professional in the areas of astronomy and astrophysics, and other like that generally happens from the ground station, and there are certain observatories that of course I'll come to discuss on that. And another part of observing space is basically you have astronomical basically payloads. So the payload instrumentation means whatever the satellite or spacecraft, that electronics part that they carry, including the microcomputers on that, the sensors, the actuators, and all types of antennas. So all these things comes into the payloads, spacecraft payloads. So over there also we have like if you have a Hubble telescope or so kind of thing. So we have some kind of astronomical observations going on the satellite and the spacecraft as well, and that gives you real deeper and precise analysis of the space, the inference from the space, and how it is expanding, and like what is happening around other planets, and what could be the lifetime of other planets, and what could be lifetime of other galaxies, and so on and so forth. There are infinite questions that comes up. There are infinite answers come up, and from that same answers again infinite questions come up. So this is again a long time infinite process that happens over here, right? So coming to let me introduce basically on the astronomy, what actually astronomy means, and what are the branches of it, and how things people are involved in these aspects, and what we can achieve through that. So starting from that, of course, like it's basically a study of universe, right? So there are people who do it completely on theoretical basis. So we used to have Einstein and those things who were the theoretical physicists, and they used to with a pen and paper, they used to with their understanding of physics, they used to derive few of the equations and create some theories based on that, right? That is one aspect, and still there are similar to the Stephen Hawking. He was again a theoretical physicist, which he explored as a cosmology in a theoretical perspective, and he used to give the ideas to other space researchers. Based on that, they used to do the research from that perspective. That is one part of it. Another part is the observational astronomy, where what happens is we actually set up a couple of telescopes, and we send a couple of satellites to the space, and we try to check for, okay, what type of observations have been happened. So for example, generally what happens is the complete chain of theoretical observation computational astronomy happens to be very well the senior astronomer or astrophysicist who possibly have worked more than 20 years, 25 years in this domain, has a thorough understanding of the depth of this physics related to space, and based on his research, he predicts some of the events that might happen into the universe, and he proposes to other facilities that, okay, I want to explore this particular kind of the event that has happened, or if it is possibility of that based on the depth of it and the impact of that particular event on the universal aspect, right? So once that theoretical has been put into this picture, the observational people will start looking into that scenario, either in terms of looking from the ground stations telescopes and observing those events that are happening, and or if it has been has a lot of impact and gets a very, very crucial information about the universe. The agencies like NASA, ESA, ISRO, they are ready to design the satellite based on those concepts and go into the space and observe those kind of things. So that is one thing, and another part is a computational perspective, where based on the theory and the mathematics that one has related to astronomy and cosmology, they derive some of their models, and with couple of things, they generate a computer model, simulation model, and try to predict or try to understand the phenomenon that is happening around the globe. So currently astronomy has been derived into these three perspectives, and of course the astrophysics part of it, of course astrophysics again is actually the branch of astronomy where more than observation and computation, and you try to, based on the data that you have got based on observation or computation, you try to inference that data and explain in a different manner that that again has a deeper understanding of the universe. So that is one thing. Now coming to the here, I'll now I start more discussing about the observational kind of astronomy, where we observe astronomy in different perspectives. So let's start with, let's say we have there are basically three types of astronomy branches in astronomy itself, right? One is called the optical telescope, optical astronomy, where we have different telescopes, and you try to see those galaxies, stars and planets and whatnot based on some distance, and based on the location you can watch the eclipses at different locations where it is visible. So based on this is a general optical astronomy that everyone can do. Even one can take a telescope like a refractor telescope or a reflective telescope, right? So which has basically a simple glass, and you have a kind of mirror over there, and you watch and enjoy that thing on that part. Of course, that again comes as a professional that I'll discuss later. Then we have something about radio astronomy. So some of the sources, some of the information that is not available from the optical view from the space, that can basically go into this radio astronomy, where you look into the RF domain. You have those huge antennas, huge arrays of the antennas, and you get a data from space at certain frequencies and try to analyze that data and predict something or infer something around the space in the same manner. Also, the sub branch of this radio astronomy comes and something called as X-ray astronomy. So here, when we are looking from the X-ray part, right, the X-ray X-band, what we have in our electromagnetic spectrum, generally, since X-rays and everything, they get blocked by your atmospheric, get reflected by atmospheric. For this type of astronomy, we have to go to send a satellite and analyze those rays and everything. So AstroSat is one of the Indian satellite which has basically X-rays over there, and there are a couple of satellites by NASA which does this X-ray astronomy. So there is another technique where we can do this X-ray astronomy, is like we have something called as a balloons with a hydrogen helium, which sends it to space, and just we cross the atmosphere, and you start observing some part of astronomy. So of course there are different layers to it, and it's a more critical kind of thing. And another thing, like one of the interesting is something called as a gravitational wave astronomy. Of course, the optical astronomy works into our your visible IR and in ultraviolet, that spectrum. Radio astronomy works in RF and your the complete other X-ray domains, right? And third part, which is something called as a gravitational wave astronomy, which is which had been predicted few years back. And the key pioneer for that is again Einstein. I'll be coming to that point in detail because it's a very very special topic, and that has put something called as some observatories around the globe, and they have detected some gravitational waves which are not comes into any electromagnetic wave. They are a different class itself, which is called as a gravitational wave, and that is another way of exploring our universe. So we'll see how that happens in a continuation with that. Okay, so coming to basically seeing this particular different telescopes. So you can see these are different telescopes across the globe, right? Huge telescopes, right? So one is the Hanley, one is in Germany, right? One is in California. There are a number of locations around the globe. So you can see the amount of the diameter that it is carrying, right? Of course, it's a standard Wikipedia image. You can search it. This is the standard telescopes across the globe. And eventually, you can see at the bottom of this, there's a huge control centers for each and every telescopes, right? So this is somewhere, our topic of discussion directly, relates for that, right? So generally, like the standard, like whatever I have read and what I know about this type of astronomical things and everything. So the size of the telescope, the diameter of that complete, the mirror that the telescope carries, right? That like it's like 12 to 13 meters itself, right? Huge size of diameter. 12-13 meters is a huge size, right, for the diameter itself. Normal telescopes that we observe, right, that comes like 4 inches, 6 inches. This is like huge meters, and it has a lot of other collection and a lot of control centers to it. So for observation and exploration of the space, right? So this is completely falls into your optical, optical astronomical kind of thing. Now coming to another part of that, radio astronomical. This is image from the Indian Center, something called GMRT, stands for Giant Meter Radio Telescope, GMRT. This is in near Pune in Maharashtra, 80 kilometers from the Pune, and they have a different antenna arrays, as you can see over here. Antenna arrays, and they collect a huge data from the space. Like it's like 12 gigabytes per second is the amount of data they are collecting and working on that. So the famous institute called the Tata Institute of Fundamental Research are involved with this. They own basically all these things, and they have a huge amount of data. And when I have visited and I have attended a couple of workshops with those people, I have seen that the FPGA cores like they use for the processing, like there are 12 to 13 FPGA, I think Spartan cores that use for just for processing a single from a single station. There's a huge amount of processing that they have, and they are future they connect to something called as a SETI project called as a search for extraterrestrial intelligence, right? So if someone is interested in something called as astrobiology, one can search for a huge amount of data coming from the space, and they need the supercomputers, massive computers with them. They still wants our computers, if we can, if we computer to be shared for them. You can just connect, be shared with those their server, and they can use a couple of your RAM for processing their data. It's a huge amount of data, but again, you have a lot of access to those kind of data over there. Right? So now this is again here the challenge is more into the RF domain, and the design engineers, they comes into the picture, and outside what I discuss here, more challenges into the optical things come into the picture. Now coming to the next level, which is called as a gravitational wave astronomy. So this is a bit less known into this the people, because it has been more explored post 2015 as a result, and let me explain the concepts behind it. What is this, and how these things work? So the idea behind that is Einstein's relativity theory he has explained that that the space and time are basically as a unified dimension. So we cannot separate space and time, right? So time, what? So for example, let's say if someone, your friend asks, okay, I want to meet you, okay. So what are the things you tell? Okay, I will meet you at this particular date at this particular time, but where? Right? So you tell, okay, this is where I want to meet you, right? So you specify something as a space and a time for that, right? This is very general, terms view I'm giving to you all people from that. But all the universe, everything works as a space and time. So what actually that mean again in a deeper sense? So assume that, let's say let's say you have a bed sheet, right? You hold your bed sheet at the four corners. You stretch your bed sheet, okay? You stretch your bed sheet at the four corners, and let's put a ball or kind of any messy object put into that that bed sheet. What will happen is that bed sheet will curve, isn't it? Depending on how huge the mass is, the bed sheet will curve over there, right? So this Einstein's theory says that the same thing happened with basically in our universe. That how the gravity has been generated is because that, imagine that Earth has certain mass. It is it is moving into the space around the sun. Now, because of the huge mass it has, the space that it is there, it is that it is curving that space. Similar to the example I gave, that assume that space is your bedsheet and you put an object into that basically bedsheet will curve over here, right? Isn't it? So same thing happens like in a real case also. We have a higher massive the object, the higher is the curve of that space. Right? So space is considered as complete like a bed or something like bed sheet of the part as a fabric of some universe, right? Now, based on this concept, he also mentioned that higher the mass of that thing, right, the higher the time it takes, right? So more the gravity, more the time you feel on that particular thing. So the time on the Earth is faster than time on the sun, right? Time on the sun the time on the Saturn, time on the Jupiter is still faster than the time of the sun, because again the mass is huge. Heavier the mass, higher is the gravity. Higher is the gravity, more is the curvature of the space, and that's why that space and time are linked to each other. Now, from that perspective, the postulate that he has said that each and every object, right, including the mouse I am carrying, including a small needle, right, are curving this space and time, right? But the result of that is they are generating their own gravitational wave. Similarly, as a human being, we are, depending on the temperature, we are emitting infrareds. So depending on our mass that we have, the amount of weight, the mass we have, we also are, curving the space around us, and we are generating some kind of gravitational waves, right? These waves are not at all related to electromagnetic waves, right? Not related to optical, not related to RF, nothing. They are the totally different kind of wave called as a gravitational waves. Now, these gravitational waves will tell some important facts about this universe, right? So, now I'll come to the point with the picture that you see. It's basically a picture of something called as a LIGO. LIGO stands for Laser Interferometry Gravitational Wave Observator, right? So this is, you can see from here the distance that it has covered. Each side distance is approximately 5 kilometers, right? Such a huge amount of gravitational wave observatory, right? This is one location. Basically, these are two locations in globe. One is at the Livingston, USA, and I think Northwest also, and one is in Hanford in the USA, right? So what happens is that based on the postulate that the Einstein has given about the space-time curve and everything, they have designed this particular, the complete observatory. One of the, yes, the government has put billions of dollars to design this particular thing, and it is so sensitive that it can detect the, we can see the width of the proton. So 10 raised to minus 22 is basically the resolution that it carries. It's such a sensitive to that. So why I'm giving this example is because the whole observatory is working on the concept of photonics, right? It's working on photonics. Okay? So I'll let you know later as I go into what is the photonics, how it's related. But this whole thing is working on the concept of photonics, and the shape that you can see, this the right angle shape, right? This means a lot in photonics, and it has been designed in such a fashion that you generate some kind of photonic circuit itself over here. So going further, like I'll be explaining now how this thing particular work, so that you will have a bit idea and our topic of discussion. So you can see over here is there are a couple of you can see the mirror on one side. Right? There are two sides. Right, at a right angle, you have two mirrors. Right, then you have a laser source and you have a photo detector, isn't it? So basically, and on the top side, what it's shown is basically the curvature of space and time. Now, the idea behind that is what I want to, what these people wanted to detect is, let's going back to this particular thing, is let's say I want to detect some ripples, some gravitational waves that has been generated into the space and that has reached to this particular point. So not only detecting gravitational waves only from the planets or something, but it is more interesting to detect the gravitational waves from something called as a black hole. So I think everyone knows what is a black hole, and everyone must be keen to know what is the black hole. So let me simplify that in a very crude manner. So assume that let's say you have the what you call, generally we use a Scotch Brite for cleaning our the vessels and everything. So assume that you have a fresh Scotch Brite, and as you keep on working on that over a period of time, that it gets smaller and smaller, right? So its volume gets decreased, but its mass does not get decreased, right? The mass remains same, its volume starts shrinking up. Same thing happened with the stars, right? So the basic qualification of a star to become a black hole is that it has to be at least 10 raised to 6 times, right? 10 raised to 6 times of the mass of our sun, right? If it is in that particular, in that range, right? It is just qualified to, be a black hole and, to become a black hole, right? There are other factors and everything, but this is a very simple way I am explaining that. So what happens is when there is an electronic degeneracy process happens over a period of time, this basically starts shrinking. This particular star started shrinking, and it runs out of the field because of the nuclear fusion and the fission reaction happening over there. Now once it is no more like a star, it basically starts collapsing from its own gravity. Now once it starts collapsing from its own gravity, its mass has not changed, right? Its only volume has changed, and smaller it has become. It is, of course, like it starts attracting the nearby objects around it, and its gravitation becomes so high that at a particular point even light cannot escape from it. So that then it is said to be called as a black hole, right? And of course there are a lot of myths around that, there are a lot of theories around that, so I want to go into that theories and everything, but yes, they do exist, and gravitational wave has basically proven that they do exist and they do collide, and they have detected something based on that, right? So so what happens is basically assume that there are higher masses like black holes, they have merged together, right? Higher the mass means they are going to generate a higher energy into the gravitational wave, and those waves are going to travel through complete space and time, right? So the idea over there is we want to check different type of gravitational waves, right, into the space, and based on those gravitational waves we try to infer something that has happened into the past. Okay, so basically on 15th of September 2015, right, this particular LIGO observatory has received a chirp of the signal, right? That was the first gravitational wave that ever received on it is always receiving, but that has been detected on the Earth itself. Okay? So what happens over there is they detected that okay, there is a gravitational wave has been detected, and they start analyzing what is happening over there. Of course, the first wave that it received were a bit of a noisy that it could not predict anything, and then they start again changing their algorithms, precising the things and everything, and eventually, I think in a next April also, I'm not sure about a date, they have received a well-known signal, and from that signal, they have inferred basically that the signal that I received, right, that signal is from merging of two black holes, right? Now, how we can say that it is based on the this particular black hole? So, based on the theory of relativity and the data that received, based on the signal processing techniques, right? Based finding FFT, finding out the frequency, fundamental frequency, and most of the things there are a lot of other the filtering aspect, lot of things are there. Based on that thing, they have found that this particular wave that they have received, right, is basically colliding of two black holes. One black hole, I think, approximately something like 0.7 into something mass of sun, and other is something 1.4 mass of sun. I'm not sure about those two those masses, but they have predicted that. But eventually, other thing that they have predicted, that based on the frequency and the other signal processing, the statistical characteristic of the signal, they have predicted that the wave that they have received, right, is 1.4 billion light years old, right? So the event, they received that signal on the day of some April on 2017 16, and the event that the wave that received, right, the event have already happened 1.4 billion light years back over there, right? So that wave has been traveling through this complete space and time. They have been received, and post to that they have received a number of signals based on that, and still they are doing it. So this is again like going again other than the photonics, this is another topic where the student from the engineering can actually be interested in terms of this machine learning and signal processing, where you can go to their website of LIGO. They have released their all data for the free, and you can use it and analyze it. You can get a fantastic predictions. Even I used to work on this particular data, and I have really got a massive results from that. The interesting facts about the astronomy and the universe, right? Very interesting topic to work on. So coming to our discussion, how this topic related to the photonics part, how these two arms that we can see that is helping to get our gravitational wave. Now, over here you can see on this right angle, there are basically these two beams, basically two branches, and there are mirrors over there, right? So now with a laser source, right, we have a beam splitter, right? It splits out, right? I'm going to discuss about the designs and everything as a component of photonics in a couple of minutes. Now over here, what is happening is the laser source, right? This laser source basically is sending a beam, and it is getting split into two parts, right? It is splitting. Now, because this is something called as an interferometer, it has some phase shift around it. Now, what happens is, if right, so the arms over here are so sensitive that even a small ripple into the space-time will make sure that this arm will change their length, right? They change their length. Now, depending on the change of the length, what will happen is the phase shift that they have received, right, it is going to change, and we receive the data from this particular these mirrors and detect on a photo detector, and based on the phase difference, we predict that whether the gravitational wave has been received or not, right? So it is technically like it's a very deep topic, but on a very general level, you can see just a movement of this particular arm will tell you the kind of the wave, the frequency you receive. And don't imagine that it is going to move like half a kilometer or 100 meters or so, right? It's a so much. It is so much basically precise and sensitive that even the smallest change of mm's and everything are able to take, and that's why we are able to detect the black hole waves, merged of the black hole waves 1.4 billion years light years back over there, right? So this is working on the something called as a Michelson interferometer based on the photonics, right? So I'll be discussing that part in a couple of slides, right? To work on, if someone other than photonics interested in this particular LIGO project, please have a look data. There are a number of open source available to that. Refer to that. There are a number of papers published based on the signal processing and machine learning on that. Kindly go through that. So now coming to exploring the space in terms of optical detection. What are different techniques? How we can explore that space? So basically, we have a photometry where we take the images and everything. Possibly a year back or so, there was a lady scientist who has taken the images of the black hole. Right, it was very famous event that has happened. So it is again coming to this photometry. Another part is interferometry. So what just now I have discussed is an application of an optical detection of an interferometer. Right? With the interferometer, you get the data and you analyze something. Then we have something called as a spectrometry. In spectrometry, you analyze the complete spectrum of the visible spectrum, IR, infrared, what not. Right? So basically, out of whole of this thing, the techniques that I have written, one of the famous is spectrometry, and it gives a lot of information regarding about the space at different wavelengths, different information in terms of so imagine that if I have a source of hot glass, I will be getting in a spectrometer, in a spectroscopy, I will be getting a continuous spectrum. Let's say then I have a hot gas with a high density, I'll get a emission spectrum. And then we have, if a cold object is there, we get a what we call as absorption spectrum. So based on these spectrums, we try to analyze what is happening at the background, and we can predict few of the things. Right? So that is one thing. Then we something have astrometry or microsensing, but related. So here what happens is in space there is something called as a gravitational wave, gravitational lensing, where imagine that you have a typical beer glass that comes with the curve, the egg-shaped beer glass, and if you observe how this not on the beer but any water you liquid pour into it, how the water looks, is kind of a lensing effect that you get from that. Same thing happened into the space because of the reflection happening. There is something called a gravitational lens happening over there. So it assumes that there is another source of light into the space, which is actually not. It's a result of something as a lensing effect that happens over there. So there are different lensing techniques available, and of course, the micro lensing is used in our case where we want to channelize our from the optics when we receive the rays of the optics from the space, right? We put into the micro lensing and to direct into the for our control circuit and to get the data from that perspective, right? So that there are typical techniques, detection techniques available from that perspective. So so you can see how the so here more I'll discuss now into terms of how instrumentation of how the electronic designs they're helpful for discovering exploring the space. So you can see the complete thing starting from a typical Galilean telescopes, Newtonian telescope, reflector mirrors, and whatnot, right? So there is a evolution that we end up into the CCD cameras a few years back, and now the era of the astrophotonics. Here, basically, you can see there are different beam combiners, photonic lantern, OS fibers. So this is still what is happening is this is again into the astrophotonics, but in terms of the kind of heavy optical instrumentation. What we are going to next is still we are going into the smaller layer of it, going to the chip level and understand how things are going to work around that, right? But the concept remains same, right? The size reduces, but the concept remains same over here, right? So this is how it has been evolved, and you can see as it has been progressed, you can see the deep depth at which we can actually go and finding out details of the universe. So at the final end, we have basically the complete the kind of structure of the universe, because of big structure of the universe, that large scale structure LSS of the universe that it is possible over here, right? Galaxies and everything. Okay, so now first of all, then what type of first of all so there are different challenges and different issues happen when we try to find out the information about the galaxies. Okay, not the galaxies in terms of the space over here, right? So I have noted a few of the very critical points that every astronomer faces those points. So let's say someone is interested in finding out the kinematic of galaxies. So what does it mean over here? So assume that it has been, some theories, and everyone says that okay, the universe is expanding. Okay, but what is the proof of that, right? The net entropy of that energy is expanding, but what is the proof of that? So we use the concept as I discussed from the spectrometry, where we have something called the redshift and the blue shift concept. So let's understand what is this. So in the physics, we have studied about a Doppler effect, isn't it? So as we can see a relative motion between two objects, the sound energies, right? As things are moving away, the frequency is right, higher, right, less, right? And as I keep, so two objects come together, the frequency, the relative frequency has been increased, of course, right? So same thing happens over here is, if you look from the complete spectrum, when the two galaxies, two stars, if they are moving from each other, right? And if we compare the spectrum, Indian spectrum of them, right? What we see is basically the red shift. It's called a red shift. We can see a bigger thing into our red spectrum. Right? Similar, if they're coming closer, we can see a big shift into the blue part of it, the blues shift over that, right? So this is one of the key things that astronomers use for checking out the complete kinematics of the galaxies or planets or something like that, right? That is one thing. Now, observing the faint sources in the universe. So there are certain sources, like as I explained about X-rays and those kind of sources, that you cannot basically get those things onto the ground telescopes. It's impossible to get into that. So we have to move to space and observe kind of things. So other than that, also there are certain sources which are very low in magnitude, very faint sources that we need to observe. And for that thing, we need to use some of the electronic design, instrumentation designs, which makes kind of filters and everything, so that makes your what observations better, right, and inference better. Then another thing is discovering the characterizing exoplanets and their atmosphere. So what are the exoplanets, the higher planets, the Uranus, and more than that, other planets that they discover, right? We want to find out something regarding that. So for that, again, we use the astronomical detection with observation in terms of optical or in terms of radio frequencies, micro frequencies, whatnot. And then we have, of course, another is always the galaxy, initial galaxies. So everyone is curious about what was the state of the universe at the beginning. Of course, since there has still been conflict about the Big Bang and something called as the steady state stellar theory, so I won't comment on that. But it has been shown that there is something called as a cosmic wave background radiation, CMBR, right? That was generated when I think the universal temperature, the temperature of the universe was, I think, some 3000 Kelvin or so, and the photons that has been released, right, they generate in a micro frequency. They had been detected at the Bell Labs, I think, in 1969. So that has given a Nobel Prize for two guys for detecting CMBR, and luckily they were the engineers at the Bell Laboratories who were doing those analysis, and fortunately they're getting some noise at those particular frequency, so that they made them to find out what is happening, and they found that okay, there is something happening at this particular micro frequency. This is called as a cosmic microwave background radiation, and that has given entry for the the starting of the universe. What was the state of the universe over there? That is one thing. Now another challenge is about always is the infrared spectrum. What NI spectrum stands for, near infrared spectrum, and there what happens is there we have a hydroxyl the molecules over there, and they because of this hydroxyl molecule background. Some of the sources, as I discussed, like faint sources, you cannot get much information to your telescopes. So you need to filter those, these optical lines from that thing. So for that, we need a good, the instrumentation that will help you out to suppress those things, to filter out something. So that they generally happens into this particular band of J and H bands for this particular wavelengths into infrared part, right? So these are the some of the challenges and techniques that people astronomers try to use to explore the space and try to find the info something from that. Okay. So now based on that, people now go for the design part of it, right? So what are the challenges currently into the design part? Of course, when I was showing you a couple of larger telescopes, the observatories that carry, right? There are huge, right, large instruments, and there, so you need a heavy electronics and heavy instruments to build on that, right? So there are different. Again, you have to work on multiband, you have to work on UV, you have to work on IR, you work on visible. So again, those part again, added a critical challenges to your designs, right? And of course, inference that I discussed from that. And lastly, any of the product always comes with the power consumption and cost, trade-off that always happens in any of the cases, right? So these are the typical challenges that over there. So now, how photonics is going to help you out in this particular regards? Okay, let me explain what is this photonics means actually, right? So as a typical definition, it's basically a material, right, that is associated basically the manipulation of the light, right, in terms of this emission, transmission, processing and direction of the light. Right? So similar thing that we do in electronics, same thing we do with the photonics. But now the design changes. So now let me give you an example that the Intel processors, right? So based on the semiconductor devices, I think after like 3 gigahertz or so, the switching speed of those processor has a limitation because of the transistor material that we are using. But what if I want to use go for a higher speed? Now I have limitation of the electronics part. So instead of going to those electronics part, people started jumping into the photonics, where everything is happening inside a chip based on the light. And the base of that is again a silicon, what you call silicon photonics, but everything is being manipulated by the light. So like we have a conducting wires and the tracks over there, right? Here we have something called as a waveguides. Similarly, as we have on the electronics, we have detectors, we have a photodetectors over here. We have a source of, as a voltage source, we have basically a laser as an active device, right? So they are basically kind of same kind of the architecture, but with a different perspective that we have to look into it. And this is more now we are going into this something called the photonics integrated circuits, which are the chips of the size, and that helps you to make the design better, make efficient, can reduce the cost for the bulk production, and of course the size. If you need reduce the size and power consumption, whatnot. So it is the main applications of the PIC, this photonic integrated circuits PIC, what we call, is that happen in telecommunication industries, and it has been widely used into these data centers, right? It's coming into the market like anything, still coming, yet to become in Indian market, but it's in near 10 years or so, we have a huge market for that, right? So this is not what I'm speaking, not only from the astrophotonics perspective of view, but in real, from starting from your sensors also, you can use these photonic circuits with the concept you design a better sensors from that, right? So coming to like what is the thought process behind these photonic circuits, photonic integrated circuits, and is basically nothing but we have a silicon substrate, and over that we have a silicon and insulator SiO, right? Now, similar to the fiber optics, we have a core and cladding. It is same thing basically. I have a cladding and I have a core. Okay? So I create a waveguides through based on this particular substrate. This is called as a wafer. This is the base of all these photonic circuits, and based on that you design something on that. Okay? Now the challenges main happening over here is about the mode in which the wave is traveling. The mode. So we have a transverse electromagnetic wave. We have a TE wave, transverse electric wave, and transverse magnetic modes, right? So what type of modes we are going to have, that is the crucial thing over here, right? Because if I have a single mode, like I have a T trans T10, whatever mode I have, that is one thing, and I can have multi-mode as well, right? So that is again a fiber optical concept. So imagine that whatever the concept that you might have learned into this fiber optic communication, most of them applies over here, but only the challenges into design starts changing over based on the size and everything. So what are the typical, when you go to the typical photonics, of course I'm giving a complete typical overview of it, as if I go deeper it will be like for waveguide itself will be a huge lecture on that. So I'll be just touching those points now. So as a fundamental components of this particular photonics is always a waveguides, right? So everything happens through waveguides. All the transmission of things happens through the waveguide. So it becomes unnecessary for that, right? Then we have the Y branches. So I'll be showing those pictures on that. So just go through it. Y branches, we have waveguide DIMMs. Then we have a grating couplers, lasers and photodetector, right? So this is the source and this is the detection part. This is for the coupling part and this is for the carrying part, right? And splitting of the things. Right? So these are the typical fundamental components into it. Out of that, these comes into the active part and these comes more into the passive part. Right? That is a branch of that. Then similar to our electronic circuits, we also have photonic circuits, right? Isn't it? Like, so we designed some kind of circuits, like we have designed rectifier, we designed coupler, optocoupler, something like that, right? We designed. So what are the fundamental circuits of the photonics? Is we have shown by this LIGO experiment. It is basically interferometer, right? That and the same this particular design, you want a small chip for detecting some kind of the optical phenomenon that has happened. And what basically interferometer does is basically it has because of the interference of the everyone must have studied about the constructive and destructive interference that will happen, and based on this constructive and destructive patterns we get some key information about the phenomenon that is happening. Right? So it's like a tool that we use. So for example, in embedded systems we use a serial port as a debugging kind of thing, or your GDB to debug your things. This is again, interferometer is a tool to explore some kind of phenomenon that is happening into this universe kind of thing, right? Then we have something as a ring resonator, which gives you a complete phase shift around that, and we have a directional coupler. So to couple the light, couple of light into different stages over there, right? Okay, so when we try to design this photonics chips, right? In respective of whatever design your application, this is a typical model that you follow. This is I'm following something from University of British Columbia. So I have personally worked with the professor Sholosky from this particular university, and they have they taught us on how this particular model works and what are the things required for the design of the photonics chips. So you can see. First, we have to look from what type of design you have. You have passive optical, electrical, or active optical, right? So that there are the components that I discussed, right? The laser, everything that comes into the active, the waveguides comes into the passive part, right? So you first have your this particular component selection models. You have to model that into certain tools, right? There are tools. I'll be discussing what are the tools available if someone is interested in this particular domain. Now, other than that, when you go to the simulation part, right, you have to do some simulation of the circuits. You build the circuits from that, as I discussed about interferometers or the ring resonators. As you keep on increasing those things, you have a higher layer of circuits based on that, right? So we can have that. And once you have designed something, you have simulated something, right? Parallelly, you have to create something called as a model, electromagnetic model for that, right? So based on the mode in which your optical wave is TE mode or TF mode, you have to use some different computational electromagnetic algorithm like finite difference in time domain, beam propagation method, different type of algorithms that are available to model your chip. So how perfectly it is, what is the response of that chip for the different perspectives over there, right? So that is one thing. Then third stage comes is once your design is ready, you basically give it to the you create a layout of that, right? So mental graphics or these things, they you create your layout into that particular with particular size and placement and everything that happens. Then you verify it and then you send to the foundry, right? You send to the foundry for the fabrication part, right? So fabrication, there are again different types of lithography techniques that they work. Now I share my experience where I have designed it and what's fabricated form. That is, I have done all these things at my own and designing. There was review, was a verification review. Everything happened. It took a lot of time for the review itself. And once your design is ready, they finally send it send it for the fabrication. So the fabrication happened in a bulk for the different people for the different regions. And once you have the fabrication done, they create a chip. Now, once the chip has been manufactured, what they do is basically they test your chip. They get the data from that chip, right? Now, this if the data is not good enough, right? They will send you the data as well as the problems with your design. You have to review your design. You have to change everything, send it back. So this cycle is happening till the time you perfect, have your perfect design. Now, once everything is finalized, again they will send you the data, and you understand what is happening inside the chip, how it is responding at different frequencies. So that data analysis part again is a very critical when you have the design of the chip over there. And then finally, once everything is ready, you can go for this packaging and the final production part of it. Right? So this is a typical flow of the photonics integrated circuit design, the complete for the development process of that. So now. This is basically a waveguides. As I discussed about the component, this is nothing but a waveguide. So if you remember, I had shown that everything is on the silicon and insulator with a wafer on that, and we have two types of waveguides, right? One is strip waveguide. Most of time we use this waveguide. This ribbed waveguide, if you see, the shape of that is more sticky kind of thing, but more crucial thing. But this is more straightforward, simple to use and design. Of course, the cost and everything that matters. Though the strip waveguide has a higher losses, but based on other design aspects, sometimes we refer the strip wave. Right? So these are typical parameters associated with your waveguides, where you must have studied about effective index and the group index. We find out the group velocity and the effective velocity of the light propagating through that particular model, right? So same thing we have to calculate for the waveguide that you are designing, right? And so for to design the waveguide, I need to be very aware of this effective index, group index based on the group velocity and phase velocity. This is associated with phase velocity. This is associated with the group velocity. How the waveguide is behaving at those particular things. Then what type of waveguide I'm going to use, strip waveguide or slab waveguides, right? And then we go for the wavelength, because as I change my wavelength from the visible to infrared, the complete design starts changing over there, right? So this is again a crucial parameter, and then we have to look for what type of losses this waveguide is giving, and based on that, if I can build those waveguides, how I will build waveguides, that will be the better design, right? So these are the typical parameters we follow. Still, there are more based on because if this is based on silicon, so we have to look for the temperature dependence and the refractive index dependence. Lot of dependence are there, but these are some of the important basic things that I have put it over here. Coming to the next one, where I was. So this is something called as a Y branch. So if you remember about the splitting that happens into the gravitational wave, these are nothing but this is one waveguide, this is another waveguide, bend waveguide, this is another waveguide, and this is called a tapering. Okay? So these is basically a Y branch that has happened, which basically when I have a laser associated with that, I inject my light into it, then I have a separation of light at two different phases from here, right? So if I put a delay and everything, I get a complete phase shift across that. But here, this is called as a splitter. If I just reverse it other way around, so if I imagine this same mirror image connected over here, what will happen is same light will again merge back into this location, right? So like a fold. So this will called as a combiner. So splitter and a combiner, they formed with this something called as a Y branch. This is another fundamental component of the photonic circuits. Okay. So they are working as a splitter and a combiner, and again they are dependent on this wavelength. This thing, right? Next part is something called as couplers, right? Grating couplers. So now imagine that you have used a spectra, this one, what you call the prism in your school days, where you see the spectrum of the white light, isn't it? So same thing over here, we use something called as a grating couplers, where you have a light coming from the source, and then you have this particular couplers with certain width and certain period, right? So the width, you can see the W, and the repetition length, what we call as a period, the grating period, right? That gives you the resolution of how things are working at the background over there, right? So depending on the frequency and the bandwidth that you are interested, you have the width, you decide the width, and you decide the grating period of that coupler. So of course there are other couplers, something like the Bragg ratings, where you won't find it uniform. Rather you will find these things very very close and other rest of the things very very far away, right? So it varies depending on the concept that on basically the application that you use over there. So it more dependent on the variation in refractive index is more crucial to that, right? Right, so this is what I'm showing is a simple version of the MZI called as a Mach-Zehnder interferometer. So you can see this is one Y branch designed, right? Another Y branch designed, and you can see it has been curved, and the length you can see observe that the length over here on this particular arm is higher than this particular length, isn't it? This particular thing. Right? So the delay that this happens is the phase delay over here is different than phase delay over here. So what happens is when I'm having a light injected into it, I'll get a constructive and destructive pattern based on the phases I received at this particular point, right? That gives you a lot of information about the event that is happening at the background. Okay? So this appears to be very very simple, but to design that actually in a tool or based on the equation, this is very very crucial. I'll tell you, this appears to be very simple. Everyone feels okay. This is like I'm just drawing a diagram or something. No. So you have to look for each and every aspect of the bend. You have to look for the waveguide, the type of waveguide that you use, what type of stripped waveguide, what type of the losses you have, what type of mode of the light you are using with the TEM. All these aspects makes this particular design ready. So sort of thought process and a lot of design thinking happens for these things to be over there. Right. So now, as just I have briefed about these components, let's understand how we can use this photonics part as a astronomical, for the analysis of astronomical part. Right? So this is what we have, something called as a spectrometers for astronomy. Right? So there are three type of famous spectrometers, which is called as the array waveguide grating, which I'll be explaining into the later stage. So I won't explain over here. So something other called as Fourier transform spectrometer. So here, in terms of as we know, the Fourier transform is used to get a frequency spectrum from time to frequency conversion, and you understand what are the dominant frequencies, fundamental frequencies, and everything. So same concept has been used to design a spectrometer for the astronomical part, and we try to understand what type of what is the behavior of those stars or planets or the galaxies at different wavelengths. In terms of optics, I use the wavelength term rather than frequency, and I understand the behavior of that. Right? And there is something called the photonic initial grating, where what happens is, as I discussed about this particular thing. Right? So you have those curved area and gratings over there, and you basically split your spectrum based on this initial grating. Right? Another complex area. Right? So we won't go into that. But again, coming to one of the simple thing about the array waveguide gratings, AWG. So it is like in electronics we study about a multiplexer and demultiplexer. It is same kind of thing, right? You can see basically this is kind of a demultiplexer where you have a optical signal received from the source of astronomy, right? Source of the light, and then you split that into basically different regions, right? Different parts over there, and then you have here this is called FPR. This is a more critical technical term in the design, so we won't go into that as of now. But here this everything is happening inside a small photonic chip of certain microns, like 400 cross 605 microns level, and this basically creates a path difference. You can see the light traveling over here is the path required for that, and compare over here, right? So there are a lot of change in the path length. Once you have the path length change, you get a complete spectrum out of it, right? Different spectrum. So depending on the wavelength that you have, you get a different spectrum out of it. You analyze what is happening over there, right? So now what is the application of that? Because this is one of the critical thing has been used into this design of the astrophotonics, and of course in astrophotonics, I'll tell you there are very few people are working, handful people are working in globe, right? Right. So one of that is one of the postdoctorate student called Pradeep Gadkini, who is working, I think from University of Maryland, and he is a fellow of NASA. Right. So I'm referring his paper for this particular design. Everything is coming from his paper, right? So he again put into this thing, right? So assume that we have a huge telescope of the size that I had shown you, of certain 11 meters of diameters or something like that. Now we have something called as a photonic lantern, where what happens is from the telescope we have to feed that particular lot of wires are coming here to feed into that single more fibers, right? So we use something called as a photonic lantern. This is again a photonics design, right, which feeds those lines into something called as a hexa bundle, and we have the single mode fiber which works on single mode of electromagnetic TE or TM mode. And once you have that, you have a Bragg gratings, right? The gratings, if you remember, I had shown you over here. Right? This type of gratings here, there we start, splitting out the spectrum, and eventually we have the array waveguide, right, which again splits your spectrum into different regions, and then you can detect it with a camera or a photo detector, and you try analyzing it. So everything again happening this inside a small chip of few microns. Right? So the beauty of that is here. So whatever the fundamental components I have discussed, so you can see over here, these are basically the waveguides. This is this array waveguides consist of the complete Y branch. It consists of beam splitters, right? And it basically generates basically the Bragg rating, different Bragg ratings. Based on that, they separate out the frequency contents, and you can get those things based on the path length. From this thing, you can basically get and detect those kind of stuff, right? This is one thing. Another is again another where this is interferometer, right? So this is not a spectrometer. This is interferometer, where the same concept of you can see the null and anti-null over here, right? So I have a telescope, right? You put that, the complete light, it channelize the light into my photonic chip. For that I need a micro lensing. Then I have a single mode fiber that supports a single mode of optics, and then here we have the design of the interferometer, where at the anti-null you will get a constructive interference, at the null you will get a destructive interference, and based on that you connect it to basically the array waveguide gratings, AWG, and then we give the spectrum of stars and planets. Of course, how I can find planet star how I can decide whether it's a spectrum of star and planet. Again, that for that you need some kind of knowledge or the domain expertise from the astronomy or astrophysics. So those people will, if we don't have that knowledge, those people will guide us in what way we need, what frequencies do we need, right? So subject knowledge is much important in this aspect as well. So this gives you the complete design of the chip and the spectrum of that. Okay? So this is one of the applications. Now, University of Caltech. This is from University of Caltech. So they are saying, okay, so what are the areas that we can cover with this astrophotonics? So on a larger scale, you can see all those fiber optics is there, with the gratings I discussed, optoelectronics, everything is there. As you go inside, you can see the applications like large telescopes, space telescopes, right? The interferometers that just now we have discussed. All these are become their applications, and inside those applications, what are the parameters that we actually look when we go for astrophotonics? So always we look for, critical is always the spectral resolution. Very critical, because we are interested in finding out the smallest event that has happened at a different frequency based on again the application and the spectrum that we are targeting. Like if I'm targeting near infrared spectrum, I'll interested in a J band and H band, and what is the resolution I'll get over there. That gives me more idea on that, right? Another part is again the photometric resolution, where we don't we basically we connect our photonics chips to the photometric the CCDs or something like that, and then based on the data that we receive, the resolution of that will be produced over there. Okay? So these are the typical thing, and finally just giving what is the typical development step of a complete photonics chip. So it is irrespective of the astrophotonics, but it is associated with typical photonics. Of course, when I'm designing this astrophotonics chips for sending into the satellites, right? The design has a different layer of it, which I cannot reveal that, because that I'm working and it has to be kept secret. So that I cannot reveal over here. But overall, the development steps for a generalized any of the application of the chip is always starting with your mathematical designs, what is the architecture, right? We have to look for the architecture and application from that perspective. Then you have different simulation tools. I'll be showing what tools are available in the next slide. You go for the simulation, you analyze what is happening over there, then you have to model that particular chip with electromagnetic solvers, with using some electromagnetic algorithms, computational electromagnetic algorithms, that gives you the idea of how well it is, solving those areas into the picture. Then we create something, a JDS file, graphical file, that you send for the fabrication, right? JDS file basically like, you have a footprint, you have that over there, and you that same thing gets reflected on the chip over there, right? And you go for the fabrication, you have a testing of your fabrication, whether that chip is working to the optimal level or not. For that, you test it, you analyze the data, right? And then based on that, recycle those things to change in the design, and this again cycle keeps on happening over there. But once again, at the last stage, when you have the data from the chip, right, it gives a lot of much information from that. So for the analysis perspective, we use a typical autocorrelation and FFT autocorrelation methods and everything, typical signal processing algorithms, to finding out what does that mean, that how the chip is working over there, right? And finally, if you're really fine, people will go for the production part of it, right? So this is the complete development steps. And coming to, if someone is interested in particular thing, so if you are interested in photonics, forget about astrophotonics, but if you are interested in the photonics domain, kindly go through these tools. Out of that, you can see various tools like IPKIS and NASCA. They are the open source. IPKIS is open source, but it has some fees. It's not free. It is open source, right? There is a difference between free and open source. But if you go for this NASCA, this is NASCA design tool. This is the open source for that. It is free for that. It works at the limit of the Python, and you can have your own libraries designed for it, and you can have your own photonic circuit design. And once you are design ready, you can have the JDS and you can send it to the fabrication lab for the thing. Now, here some of the people who are interested in design can work. They can take up these tools and start working on equations, understand the concept behind it. Another area where people can work who are not interested in design but modeling part of it, they can actually looking into the electromagnetic solvers. So there are a number of computational electromagnetic algorithms. So you can develop your own algorithm based on the mathematical thing, and you have a better solving capabilities. Then there are people work in the fabrication. I am not much aware of fabrication methods because I have not done it. I have get it done, and I know few factors, but I don't have the depth of the fabrication. So I don't know much about fabrication, but it is still, it's a area where you can focus on to it. And finally, the data analysis technique is like, it's fabulous. It gives you a lot of understanding of the what sequence everything is doing. So the typical data science techniques that you use, you can apply into that particular thing. Okay, so this is the overview of my topic on this particular thing. So if someone interested, we can have questions. I hope Mukesh is okay. It's done.
Yes, sir. Hello? Yes, sir. It was indeed. Yes, sir. Hello. Can you hear me?
Yeah. I can hear.
Yes, sir. It was indeed very wonderful, and I must say, deep tech oriented topic and domain, and people like might have got like very good insightful thought and opportunity kind of thing in the coming years for this topic. So we are waiting for like 1 minute. We'll wait for some questions. If anyone have that kind of question, they can directly ask.
Sure.
So we'll be waiting for like 1 minute.
Yeah,
if participant want to ask some questions, they can ask. So I think we're not having two domain and like too focused on the deep techs. I believe so, but let's hope that we'll be having them, and if we have, then we'll take it. So
Yeah.
astrophotonics, rise of integrated photonics in astronomy, and perhaps one of the oldest scientific endeavors, has always sought to take advantage of new technology. After the spectacle makers Hans attempted to patent his refracting telescope, Galileo moved quickly to build his own device to study the night sky, and the rest, as they say, is the history. So, after almost 3.5 centuries after Galileo's death, astronomy continues to rapidly evolve with advancement in technology, machines, and non-scientific languages. Huge opportunities and possibilities are yet to untap, and with advancement of ISRO making announcement for public sector to use its facilities, possibilities are definitely endless now. And I'm hoping that with deep tech and like tech-driven startups to be focused by government of India with new policies for startups and all, people will be moving toward this domain in the coming years, and so I again thanks to you for taking out your valuable time, sir, and for
Thank you.
giving this spectacular presentation and like core tech oriented subject in such a smooth and such a flexible manner. So I'll just check if Dr. Samuel is also with us. Samuel, sir, you are over there?
Yes, sir.
Yes, sir. Samuel, sir, handing over to you for your
Yeah.
concluding remark.
Okay. Okay. Thank you, Yashodhan sir, very much.
Yes.
Thank you.
Thank you, sir. Thank you.
It's a very, very like a different topic for our audience, and I am
Yeah.
very sure that some participant will get benefited from this topic and
Yes,
will
yes,
try
yes,
to enter in this field, which is very different. So
yes.
I thank you, sir, to
Thank
find
you so
out
much, sir.
things for us. Thank you, sir.
Thank you very much.
Thank
Thank you once again,
Thank
sir.
Yes, yes. Thank you, Mukesh. Thanks a lot for inviting me. Right. Okay.
Sure,
See
sir.
you off the screen.
Thanks, sir.
Thank you.
Sure,
Yeah.
sir. Sure,
Okay.
sir. Okay, sir.
Thank you. Yeah. Bye. Bye.
Tomorrow we'll be again connecting on YouTube and Facebook at 1 p.m. with Miss Sakshi Gupta. She is the assistant professor at Gafigara University and will be taking a topic on rainwater harvesting. So, participants are requested to make the attendance on the link which is on the live session, and this link will be activated for next 30 minutes. Okay, Samuel sir,
Okay. Thank
can
you,
we end
Mukesh.
the broadcast? Thank you so
Yeah.
much, sir. Thank you, sir.
Okay.